Okay, so prior to our exam disrupting everything, we were talking about convection and specifically external flow. So external flow is covered in chapter 7 of the book, and external flow means flow that's unbounded. It's going around an object or over the top of an object, but it's not going in or through an object. Chapter 8 will be on internal flow, which is where we'll talk more about flow through pipes, and you'll be able to make better connections to your fluid mechanics class. So I wanted to review some of this stuff, especially after grading your exam. I'm going to try and be extra repetitive. So this slide is super important. This outlines the procedure. So convection, a big part of what we deal with in convection is going to be finding H. So H is our convection heat transfer coefficient. Up to this point, H has just sort of been given to you, and you might use it in an energy balance or at a boundary condition. But now we're actually going to figure out how do we calculate H. So our basic procedure will be first we evaluate the geometry of our system, evaluate the fluid and flow conditions. So what's our Reynolds number, what's our Prandtl number, and then we're going to find the appropriate correlation to use to find the Nusselt number. So you can think of the Nusselt number as sort of a dimensionless heat transfer coefficient, and we'll get into a little bit more about where these come from today. So then once you find the Nusselt number, you back solve to find your H, just like shown in the writing there. So these correlations are going to look something like this. These are just examples. This is not comprehensive. As you read through the book and as you solve homework problems, you'll find yourself reading more about some of the simplifications and qualifications for using that particular correlation. So this is just a few examples. So we might have, under that restrictions, we might have a flat plate with undergoing laminar flow over the top of it, and it's isothermal. If that's the particular case, then we could apply this correlation, which is going to give us our local heat transfer, well, our local Nusselt number, which we can back solve for our local convective heat transfer coefficient. Then, or we could use this other correlation, which is just an integration of the first, which is going to give us our average. So how do you tell the difference between an average Nusselt number and a local Nusselt number? Yeah, so it's denoted with the bar over the top if it represents an average. So one of the important concepts is that while we've treated convection as just sort of a constant so far, really the value of your convection coefficient can change depending on where you are on the solid. So that's where the local would come in handy. Often we may just make the assumption or the approximation that convection happens evenly, in which case we'd want to use the averages. So we're going to look, so bear with me. I am going to focus on some of the more interesting and important concepts, but a lot of what we'll see in chapter 7 and 8 and 9 and 10 are going to be these correlations, which are generally empirical. They're kind of big, ugly equations, not the funnest thing to teach, but there is some really good stuff in here. Okay, so I'm going to cruise back through. So we started looking at these different dimensionless numbers, and we were talking about, we focused specifically on the Prandtl number and the Nusselt number. So we looked at these interactive problems, and we talked about the velocity boundary layer and the thermal boundary layer. Can someone explain to me or to the class, what the velocity boundary layer, what does that mean? What is a boundary layer? Yeah.
Velocity boundary layer, kind of that, the front where there's a velocity distribution of the fluid in a pipe. So the velocity boundary layer is that part.
Okay, great. It describes the velocity boundary layer, what describes how velocity is changing when you get really close to a surface. Where often we've just made these assumptions that convection happens between a surface and this bulk fluid, and we treat that bulk fluid as just being uniform. So the velocity boundary layer describes what's actually happened when you get really close to the surface. Okay, mathematically, do you remember how we defined the thickness of the velocity boundary layer? Yeah. Great, yeah. So if we have so Alex, sorry for recording purposes, Alex said velocity is the velocity boundary layer thickness is where the velocity reaches 99% of the bulk fluid velocity. So if we had uniform flow coming and encountering a simple object like a flat table, that uniform flow is going to develop a velocity profile because the flow immediately closest to the surface is going to have a velocity of 0, assuming a no slip condition. So getting from that 0 velocity for the layer of fluid that's immediately touching the table and the bulk fluid, there's going to be some transition. So we would define the boundary layer because under ideal circumstances, that velocity boundary layer would just asymptotically approach the bulk velocity. So in order to make that more of a finite thing, we just say when it gets to 99% there. Okay, so similarly for a thermal boundary layer, there's also, if the table is heated and there's heat transfer going on, then you're not just going to go instantaneously or suddenly from the table's temperature up to the bulk fluid temperature. There's going to be a transition. So the thermal boundary layer describes what happens right near the surface of the table. And similarly, the thermal boundary layer thickness is basically when the temperature gets 99% of the way to the bulk fluid temperature. So really there are some kind of microscopic things that are happening with convection. So we looked at this number called the Prandtl number, and we did some interactive problems. So the Prandtl number is the ratio of momentum diffusivity. So that describes how well momentum propagates through a fluid. So something that's really viscous is going to have a really high momentum diffusivity. Actually, the term, the kinematic viscosity, is the momentum diffusivity. So for a fluid like oil, momentum is going to, it's really quite viscous, so those individual quote-unquote layers of fluid are going to be grabbing onto each other, and it's going to form a thicker momentum boundary layer, velocity boundary layer. Whereas a fluid like air is going to have a much thinner, and you'll have to notice the two different scales here. And for this particular example, we had air and oil each flowing at the same velocity. So this Prandtl number tells us how well momentum is going to propagate through our fluid versus how well heat is going to propagate through our fluid. So you notice oil has this very, very high Prandtl number of 6,400, whereas air's is less than 1. So orders of magnitude difference, and that manifests itself in the relative thicknesses of the two boundary layers. So oil, which has a much higher momentum diffusivity than it has thermal diffusivity, ends up with a much thinner thermal boundary layer than its velocity boundary layer. So just trying to help put some physical meaning towards some of these dimensionless numbers that we're covering. So even in that example, if we go through the actual correlation, so we went through this little test and we looked at the flow conditions, we found the appropriate Nusselt number correlation. So that's right here. This is the correlation we would use for an isothermal plate with laminar flow, and this one is local specifically. So this is going to give us Nusselt number as a function of x. So we plugged in this equation, and that gave us our Nusselt number, and then we back solved for h, just like in that procedure. So when we actually mapped out the local heat transfer coefficients of air versus oil, there are other things that come to play in here. So it's not just the Prandtl number, a bunch of other factors like thermal conductivity. So we see that the oil still has a much higher local heat transfer coefficient across the board than air. But notice how h varies with distance down the plate. Okay, so let's do these. Okay, so now let's look at solving an interactive problem. So if air at 300 Kelvin is flowing at 1 meter, no, wait, did we do this one already? No, we didn't. Okay. If air at 300 Kelvin is flowing at 1 meter per second over a flat plate, at what velocity would the oil need to be in order to have the same Reynolds number as the air? So the definition of the Reynolds number is given here, and we have a specific x given. So how fast does oil need to be flowing so that it has the same Reynolds number? And then while you're at it, you can answer this second question. They should both be open to you. So with the air still flowing at 1 meter per second and the oil flowing at whatever velocity you just found, so that the Reynolds numbers match, which fluid do you expect to have a thicker velocity boundary layer? Oops. What? Yeah, that one is new, I believe. It's Greek. Where the velocity is actually is u infinity. Okay, so these are the two kinematic viscosities. I hope that no one's confusing those with velocities, whereas u infinity is the actual velocity. Okay, so let's take a look. Okay, in the interest of time, we're going to look at these answers and move on. So I believe 34.6 meters per second is the correct answer. So the point here is, actually, let's go to the next question before we get to the point. So of the two, which is going to have the thicker velocity boundary layer? When they're both flowing at the same velocity, the oil had a much thicker velocity boundary layer. Okay, so the correct answer here is that they'll both be the same. So if we equate their Reynolds numbers, if you remember that the correlation that gave us the velocity boundary layer thickness, or delta, is a function of only the Reynolds number, and so the velocity boundary layers will both be the same. So this highlights some of the value of using these dimensionless numbers, where you're considering multiple factors and lumping them into a single number. It lets you compare things a little bit easier, and that helps to make these correlations that we'll talk about a little more uniform. So let's go back and find that slide. Okay, so remember, delta is equal to 5x times the square root of the Reynolds number. So delta is only a function of the Reynolds number. So when we put them both on that same basis, then they have the same boundary layer thickness. So as our Reynolds number gets bigger, as our flow gets higher and higher and closer to turbulence, then our boundary layer actually gets thinner because that momentum, I guess, is swept away easier. Yeah, Donovan?
And is delta the value for the boundary layer?
Yeah. Delta is the velocity boundary layer thickness. There's also delta sub t, which is related by this correlation here. That's the thermal velocity boundary layer thickness. Okay. All right, so that example, we use a correlation for laminar flow. That was solved, just that simple little correlation was solved analytically, and that's like pages and pages of math where you're solving the continuity equation, momentum balance, and thermal energy balance all simultaneously. So now we're going to move on to turbulent flow. So at turbulent flow, that critical Reynolds number for flow over a flat plate is 500,000. So get that 2,000 number is in your head because of flow through a pipe. For flow over flat plate, it's a totally different system, and that Reynolds number still has a lot of meaning, but there's not much meaning in comparing the two different scenarios. So turbulent flow gets a lot more complicated than laminar flow. Generally, you can't find analytical solutions, so typically the correlations involving turbulent flow will be empirical correlations. So who knows what that word empirical means? Yeah, based on an experiment, based on collection of just data from running the experiment, and not necessarily informed with a lot of fancy theory or math. So the empirical method for finding the Nusselt number is going to involve setting up some sort of experiment. So you're going to collect data, you're going to vary the flow, you're going to probably try different fluids that have different thermal properties, like different Prandtl numbers and different Reynolds numbers, different viscosities. So you'll do this experiment, and then you'll set up some kind of correlation that might look like this. And it's been found that Reynolds number is obviously really important in determining what your Nusselt number is going to be, and Prandtl number is also really important. So typically the correlations will have Reynolds number in them and Prandtl number. Then these other coefficients, C, M, and N, would be found by doing some sort of curve fitting. So you'd do this, you'd collect a bunch of data, and when you're dealing with different fluids, you're going to get differences in the data, distinct differences. But when you lump the parameters together, then you can see that they all line up. So that's why things are generally expressed in terms of Reynolds number, Prandtl number, Nusselt number, because those tend to sort of unify some of the effects. So your correlation, if you did a bunch of experiments with air and did a correlation, well, your results would probably just apply to air. But if you did experiments with a bunch of different fluids and lumped the parameters together and solved the correlation so that it can include the properties of all the different fluids, and you can get a more uniform and universal correlation of this form. So for turbulent flow over a flat plate, these are the really fun lectures. It's hard, man, you guys just got an exam, and now we're getting into this really awesome math of convection. So here's what the correlation looks like. I'm not going to focus much on the friction coefficient in this class. We'll focus mainly on just the heat transfer stuff. So when the flow is turbulent instead of laminar, our equation looks really similar, except that our Nusselt number has a different correlation. So this is the value of the Nusselt number, the local Nusselt number when the flow is turbulent. So if you remember, that Reynolds number, if you have flow over a flat plate, the Reynolds number is no longer constant. It's a function of x. So your Reynolds number will grow. So at some point, as that boundary layer gets to a certain thickness, you're going to start to have flow that circles back, which is turbulent flow, because the boundary layer has gotten so thick that it can't stay in this nice layered smooth form. So you may have flow that actually transitions to laminar or turbulent just from going from x equals 0 to x equals the full length of your plate. So what that means for us mathematically is that we'll have to take some sort of average between the two. So for the first part of the plate where the flow is laminar, we'll have to apply a laminar correlation. Then for the later part of the plate when the flow gets turbulent, we would apply a turbulent correlation. And if we wanted an average of the two, we would do these average parameters, which involves that integration that we've covered. So that would just have us take the average of the laminar region and the turbulent region by doing this double integration. That has been put into equation form. So this particular equation would give us the average Nusselt number when there is mixed flow. So specifically this constant here, this 871, arises from having a critical Reynolds number. That's when you reach your critical Reynolds number and you transition from laminar to turbulent. There may be instances where the flow gets tripped, which means, let's see if sometimes you can induce turbulence in other ways by having something that will disrupt the flow, in which case you'd need to solve for a different number that goes here. So this 871 specifically means the natural transition of flow from laminar to turbulent. But if turbulence is forced in some other way, by having a plate or something that blocks the flow and makes it go turbulent early, then we'd replace that number with a Reynolds number that corresponds to the point at which our flow was forced from laminar to turbulent. So for example, if I introduced some sort of blockage here, or maybe I put like a grate here, that would naturally induce some turbulence. So if we made that assumption that as soon as our flow hits the leading edge of the table, it became turbulent, we would just use a pure turbulent correlation, and this would just go to 0. So you'll have some homework problems dealing with that kind of situation. Okay, there are other, and here's if the boundary layer is tripped at the leading edge, then the critical Reynolds number is just 0, or the critical Reynolds number would correspond to whatever x at which the flow is forced to be turbulent. So there are different scenarios here. I've given you this example where we have flow go over a table, and then when we talk about heat transfer, we say that that table is heated. So there might be something called an unheated starting length, which is where maybe the table is just the same temperature as ambient, so it's not being heated, which means that your velocity boundary layer will start to develop, but your thermal boundary layer won't develop because there's no heat transfer happening. So in this particular case, you'd have your velocity boundary layer form on the unheated section. So this zeta squiggle thing is the unheated starting length. Then when you get to the point at which the table is heated, then your thermal boundary layer starts to develop. So there are different correlations for this particular scenario. So when you have an unheated starting length or uniform heat flux, the correlations would be of this form. Then we would get our coefficients. So UST stands for uniform surface temperature. Here's uniform surface flux. If it's laminar, there's a different correlation. And if it's turbulent, there's a different correlation. And then this zeta term in here would be the distance of your unheated starting length. So you're starting to see sort of the nature of these correlations. There's all different kinds of scenarios, and you got to just recognize what your scenario is and carefully apply that correlation. And I try to be, on exam problems especially, I really don't love having you guys memorize equations. So certainly these correlations would be provided for you, but there is going to be some effort in knowing the different scenarios and knowing when to apply what correlation. Okay, so in terms of our, we'll skip that. I'm trying to get through this stuff. So there are other scenarios. Remember, this is external flow. So flow over the top of a plate would certainly apply as external flow. You can also have flow around other geometries. So a common one would be a cylinder in cross flow. So you have a cylinder, this big circle would be a cylinder coming in and out of the screen, and then you'd have flow going around it. So this actually becomes quite a bit more complicated than the flat plate, because now on the back side of this you start to get this turbulence building up. So these correlations, the actual physics of this system is much more complicated, so we're going to go to purely empirical correlations here. But the Reynolds number we'll use will depend on the diameter of the cylinder. And again, this is totally different than flow through a pipe, because this is flow going around a pipe in cross flow. So while the Reynolds number is still defined with that very nice rho VD over mu, the value at which flow transitions from laminar to turbulent will be different. So we have the Churchill and Bernstein correlation that gives us our average Nusselt number. So again, we're not going to particularly care about all the different local things. So certainly heat transfer is going to be different on the front side of the cylinder where the flow is more laminar than on the back side where it's more turbulent. That's going to be outside of the scope of this class to figure out a different heat transfer on one side of a cylinder versus the other side. So we'll typically just use this correlation, which gives us the average Nusselt number. And again, while this functional form is a little bit more complicated, notice that it's still purely a function of the Reynolds number and the Prandtl number, and then a bunch of other constants. So another instance where instead of having flow around a cylinder, you could have flow through a whole bank of cylinders or through a whole bank of tubes, in which case you need to pay attention to the interstitial velocity, which is this V max. So if you have a uniform velocity, when it encounters this bank of tubes, that flow is going to have to squeeze through the individual tubes. So the cross-sectional area available for flow gets smaller, which means the velocity, the local velocity going in between those tubes is going to be faster. So these correlations will depend on the different spacings between the tubes, and then this interstitial velocity, which is denoted here as Vmax. So here's the Nusselt number correlation going through there. So we get our average Nusselt number when we have an isothermal array of tube banks. All right, so now let's get to, now that I've bored you with a bunch of different correlations that I don't expect you to memorize, why would we care? I mean, we looked at some seemingly kind of weird geometries. Why would you care about calculating heat transfer across tubes? Where would you encounter that physically? Yeah, James? Okay, pretty much every air conditioner ever. Great, thank you. Can someone be more general? A heat exchanger, yeah, so we'll get to heat exchangers. So a heat exchanger, that's chapter 11, that comes after convection. So a heat exchanger is a device that's designed to transfer the maximum amount of heat. So according to Newton's law of cooling and every other heat transfer law, the total rate of heat transfer is proportional to the surface area over which heat transfer occurs. So for convection, we would want to increase the surface area. So this becomes actually super important if you become a design engineer or even a process engineer where you'd want to characterize the performance of your heat exchanger. You'd need to know what the heat transfer coefficient is on the outside so that you could figure out how well is that heat exchanger going to perform, and more specifically so you know how big to make that heat exchanger, how much surface area do you need, because the better the H, the higher the heat transfer coefficient, the smaller your heat exchanger has to be, which is going to come down to dollars at some point. Okay, so once we have H for fluid flow through banks of tubes, how would we get the total rate of heat transfer? So we're getting into, I'm trying to introduce a much more important concept that will be definitely something that shows up on exams. So let's say we have our flow here, and that's going to be at entering some initial temperature, and that's going to be flowing through this large bank of tubes in cross flow. So how would we go about, so using H, how do you typically get Q? So you'd use Newton's law of cooling, right? So one of the tricks here is that the air temperature is going to change. This is a heat exchanger. It might be designed to specifically heat up that air. Maybe it's your home heating system. So your air temperature is physically going to be increasing as a function of distance as you go through here. So that implies that we're going to need to do some sort of integration. So Newton's law of cooling, which is, let's just do flux is equal to H times delta T. And that delta T is going to be our surface temperature and our bulk fluid temperature. So this Ti is basically going to take the place of our bulk fluid temperature. Or this, yeah, let's call this, I'm going to call this Tm. So this Tm, and in later lectures you'll understand why. So this Tm is going to be our fluid temperature. So Newton's law of cooling, if we took a little slice of this system, Newton's law of cooling would apply locally. Where our flux, we could find our flux right there. So that's going to be equal to H times the tube surface minus our fluid temperature, T sub m. But notice that because our fluid temperature is going to be increasing as we go down the length of this bank of tubes, our flux is going to be changing. So that's going to imply that we're going to need to do some integration down the whole system. And I promise you I'm going to ask you some questions like that on homework and exams. Okay, so if the tubes are all at a uniform temperature, how do we expect the temperature of the fluid flowing across the tubes to change with respect to X? So let's say here is X. X is the distance down this bank of tubes. And then we're going to plot this T sub m, which is our mean fluid temperature. How do we expect it to change? Let's say our Ts is up here. And then our entering temperature of the fluid. So this is our surface temperature. This is the temperature of the tubes. This is our entering temperature of our fluid. How is that temperature going to change as it travels through this bank of tubes? Do you think it'll be linear? Okay, great. So it's actually going to increase, assuming that our surface temperature is constant. So here, right at the beginning, our temperature driving force is the greatest. So our flux is going to be highest right there, which means our temperature is going to increase the fastest. So after our fluid's been heated up a while, let me draw that a little better. So after our fluid gets higher, because these tubes are heating it, our driving force now is going to be smaller. So there's going to be less flux, which means our temperature increase with respect to x will get smaller and smaller until the point that our fluid temperature reaches the surface temperature and there's no more heat transfer happening. So this implies that we're going to have to use a new form of Newton's law of cooling, one that represents the integration down the whole length. And then we're going to get into something called the log mean temperature difference. So it's still, temperature difference is still our driving force for heat transfer, but now it's a log mean temperature difference. So it's basically integrating all those smaller temperature differences down the whole length. Anyway, thank you very much for your time today. We'll get more into this stuff on Friday.